So thank you very much for introduction, and thank you to the organizing committee. It's a great initiative, I think. So as a first speaker, I don't quite know where to start. So I tried to put some slides together and explain about basic DNP mechanisms, and I tried to include some recent work from 2020, in fact. So today I'm going to talk about hyperpolarization methods, mostly in the context of magic angle spinning solid state NMR enhanced by DNP. Let's start by asking, what is dynamic nuclear polarization and what is its connection with EPR and NMR? Here, I assume that most of you are familiar with these techniques. So under magnetic fields, spins tend to split in energy levels by Zeeman interaction. And the extent of this splitting is given by an intrinsic factor called gamma. For electron spins, it is a much wider range that falls in microwave frequency. For nuclear spins, it falls into radio frequency. So that's the reason why for EPR we use microwaves and NMR we use RF. The second key difference between electron and nuclear spin is the spin polarization, which is again based on its intrinsic gamma factor and inversely proportional to temperature. So if we were to plot for a constant magnetic field, temperature versus spin polarization, we clearly see that, for example, here, protons are way less polarized as compared to electrons. And this brings up the sensitivity issue in NMR. Because of its intrinsic low gamma, it requires a lot of experimental time to obtain useful signal because the signal is inherently low. On the other hand, unpaired electrons have orders of magnitude higher polarization. So what can be done is use hyperpolarization. So by irradiating microwaves on a sample that contains electrons embedded in nuclear spins, polarization can be transferred to the neighboring nuclei, and therefore signal enhancement can be obtained on the nuclear spins with a better sensitivity. So this idea was discovered a long time ago and has been developed after that. The very first measurement was on conducting electrons in lithium metal. So in the metal, conducting electrons polarize lithium-7 spins. And as you can see in this figure, there is increase in NMR signal. And this experiment was done at very low magnetic fields. After that, conduction electrons from sodium have been used. Trapped electrons in diamonds have been used to polarize and increase sensitivity on carbons in the diamond, for example. After that, further developments come mostly from the technological development in superconducting magnets and high power microwave sources called gyrotrons. This is it's really a history of innovation where the community went from very low magnetic fields to high magnetic fields as high as 21 Tesla. After the 5 Tesla barrier was crossed with the help of gyrotrons, especially in the context of MAS DNP, we were able to look at frozen solutions, polymers, material surfaces, proteins, even in-cell DNP is possible so far. So in this journey of advancement in technology and understanding the theory of DNP, people developed techniques and polarizing agents. Of course, there are many hyperpolarization methods possible. Some of them will be discussed in future tutorials. For today, I am going to talk about magic angle spinning solid state enhanced NMR by DNP. So yeah, the basic difference between conventional NMR and DNP enhanced NMR is that in addition to the NMR magnet, there is also the gyrotron, which is a microwave source. Microwaves are fed to the magnet through microwave transmission line. And these experiments are performed at cryogenic temperatures. Remember the spin polarization versus temperature. At lower temperature, there is higher spin polarization. So we go for cryogenic temperatures. Formulation of a sample for hyperpolarization is the key to get hyperpolarization on the sample. And it requires, obviously, first the microwave, and secondly, the sample formulation that contains unpaired electrons. We call them polarizing agents. It could be either metal ions or organic radicals of different types. And second factor is cryoprotection. Because we are working at 100 Kelvin, it is essential to avoid formation of ice crystals because we know that by experiments that formation of ice crystals prohibit the transfer of polarization further in the sample. So what we aim for is aqueous or organic solvents that form amorphous uniform glass instead of ice crystals. As an example, let's take a look at a MAS DNP experiment where we polarized proline with TACpol biradical as the polarizing agent in organic TCE. And by looking at the difference in microwave off to microwave on spectrum, it becomes clear that in experiment, so for example, here enhancement of 300 means a lot in time saving. This experiment took us 3 minutes. Without DNP, it would take 2 months. So for systems where signal of NMR signal is very low, it is imperative to use DNP to obtain useful information. Next, we are going to talk about how does the polarization transfer happen in a cryogenic system and what are the DNP mechanisms. I would like to take a pause and invite you for questions. Daphna?
Does anyone have any questions?
Do we need to unmute people?
You can either message me and I'll unmute you, or you can raise your hand. It looks like everyone's okay so far with the introduction, so we can keep going.
Okay.
Thanks, Manu.
Right. So DNP mechanisms, what are they? There are 4 DNP mechanisms possible. And which mechanism is active in a sample in a system at particular field or experimental conditions depend on several factors. First is property of the polarizing agent. Is it a biradical? Is it a monoradical? Is it a metal ion? Where is it localized in the sample? Is it forming clusters or not? Because that would change the dipolar coupling. Second is EPR properties that include G-tensor, line widths, relaxation times. For example, here totapol has G anisotropy and therefore it has this broad EPR line. In comparison, BDPA and trityl have narrow EPR lines. The third factor is microwaves. It's frequency and power of the microwave. And the last one is temperature. I am going to start by introducing what is solid effect. And this is a mechanism mostly invoked by monoradicals that have narrow EPR line width, such as trityl. It's essentially a two-spin system where electron and nuclear spins interact in the presence of microwaves. This matching condition with microwave is important. It has to be fulfilled for solid effect to be active. In terms of energy levels, it is based on forbidden transitions, so double quantum and zero quantum. And because it is nominally forbidden, it requires high microwave power to be effective. So coming back to the matching condition for solid effect. In most cases, it is far more easier to change magnetic field. So if we plot enhancement by DNP as a function of DNP, so as a function of magnetic field, we see that there are areas where enhancement is maximum with a negative sign or maximum with a positive sign. The position of this maximum positive and negative lobes with respect to the EPR line is characteristic of solid effect. So for a nuclear alarm frequency of proton, it should be separated by 400 megahertz at 9.4 Tesla. So DNP field profiles can be simulated based on EPR lines using this formula, which is essentially the zero quantum and double quantum, the difference between zero quantum and double quantum transitions. The second effect is cross effect, which is a bit more complicated. It is evoked by broadline biradicals, such as totapole or amupole, that have broad EPR line. So homogeneous line width is smaller than Lamarck frequency. And so coming back, dipolar coupling is the key for cross effect to take place. And it is often induced in the system by attaching to nitroxide moieties with the linker so that there is a certain fixed distance between the electron spins for dipolar coupling to take place. Cross effect is invoked by a mixture of solid effect of single quantum, zero quantum, and double quantum. And it is, again, can be simulated by using this equation here. If we look at the DNP field profile and compare it with the nitroxide EPR spectrum, we notice that the two electron spins that are involved in this process must be separated by the nuclear alarm frequency. And those are the positions where we get maximum positive or maximum negative enhancements. So based on the theory of cross effect, there has been evolution in the design of biradicals for DNP. For example, we went from monoradicals, so tempo, to BT urea by attaching via a linker that is flexible. And experimentally, we found that people found that increasing molecular weight or bulkiness of these groups near nitroxide moieties tend to increase enhancement by prolonging the relaxation time. Another design is by increasing again the dipolar coupling in a rigid molecular structure such as BTBK, and working again on bulkiness of the groups near nitroxide to find optimum combination of relaxation times and dipolar coupling. So far, amupole and techpole are the best performing polarizing agents, radicals at 9.4 Tesla. Here is an example of how can we distinguish different DNP mechanisms by looking at experimental field profiles. Here we are looking at EPR lines of trityl and VDPA. This is overlaid with experimental field profiles for protons. And just by estimating how far is the nuclear alarm frequency, we see that maximum for solid effect condition is replicated in the experimental field profile. So by overlaying simulation and experiments, we can tell that this is a solid effect condition in both cases for trital and BDPA. However, by using a mixture of radicals, there was a huge increase in enhancement, which is also again a characteristic of cross effect because it is an easier mechanism to evoke. It requires less microwave power. And also it is more probable because it is the allowed transitions nominally. So in a mixture of radicals, there is the dipolar coupling introduced between BDPA and trital just by mixing the two. And there is a significant overlap in EPR spectra that allows for cross effect to take place. Other experimental DNP field profiles gave us a portfolio of different radicals and which DNP mechanisms they evoke, and made us better understand the mechanisms of DNP in magic angle spinning. At the same time, it also evoked some questions such as, okay, there are the maximum negative and maximum positive enhancement for BDPA. What is this little thing in between? This is not characteristic of solid effect. So investigations so it was investigated at MIT. And in this process, we now better understand DNP mechanisms. Here I am now moving to, from what we know as DNP mechanisms, solid effect and cross effect for MAS DNP. Recently, there have been developments in terms of polarizing agents and in terms of the DNP mechanisms. Let me first go with polarizing agents. This is, here what we are looking at is hybrid biradicals. And the reason for going to hybrid biradicals is our best performing ampole and techpole perform worse at higher magnetic fields. So at 9.4 Tesla, they perform well, but at higher magnetic fields, they tend to not be as good. So the idea was to combine a narrow line EPR radical and a broad line EPR radical. And in the process, engineer a linker length so that dipolar couplings is optimum, as well as bulkiness of the R group that control electron relaxation times. This was a series of hybrid biradicals investigated in our lab by Dorothy Wieser, and HITECH 2 was the best performing so far. So clearly it gives us information that going from DNP mechanisms, understanding them well, we can use this information to design better polarizing agents and use it in applications to investigate surfaces and structures by NMR. Another recent discovery was Overhauser effect in insulating solids. Earlier, Overhauser effect was thought to be present in liquids and conducting solids because they satisfy the condition of fluctuating hyperfine interaction, which is satisfied in liquids due to molecular tumbling and in conducting solids by translation motion of electrons. However, in insulating solids, it was not thought to be applicable. But as we will see that this position has changed. Let's first see what is our Overhauser effect and where the DNP field profile should be. Here it's a two-spin process And the matching condition is that microwave power should be equal to, frequency should be equal to the Raman frequency of electron. And therefore, in field profile, the DNP field profile is at the same position as the EPR line. It essentially works by the difference in relaxation rates. And this Oberhauser effect is a simple zero quantum or double quantum effect, where this difference in rates can lead to either positive or negative enhancements by Oberhauser. In 2014, it was discovered by Kan Hu that if you put BDPA in polystyrene, it is possible to evoke this very distinctive enhancement at the EPR line that comes from Oberhauser. In theory, so the experimental results also go well with the theory, say, in the sense that Oberhauser effect scales linearly with magnetic field. So this is one way to perform experiments at a high magnetic field, is to use Oberhauser effect as DNP mechanism. This case is special for BDPA because BDPA has a delocalized electron that is coupled with protons present in the organic structure, and there is fluctuation in anisotropic and isotropic couplings that lead to the fluctuating hyperfine interaction, which is essential for Oberhauser effect. So that being checked, now let's move to thermal mixing, if it is possible in MAS DNP or not. And we came across recently this publication that is quite recent. And it appears that if we match conditions for thermal mixing, it is also applicable at MAS DNP. So what are the requirements for thermal mixing? That it is a multi-spin process that requires high concentration and low temperatures. The rule of thumb was less than 6 Kelvin, thermal mixing is possible. It is a classical phenomena that works with different spin baths, so electron Zeeman bath, dipolar coupling, and by thermal contact with the nuclear spin bath, it transfers polarization or spreads polarization in the sample. So here, what Asif Iqbal from UCLA found that by increasing concentration of trityl from 10 millimolar to 100 millimolar, there was complete lack of the negative and positive lobes from DNP profile. So it appears to be a crossover from cross-effect condition to increase in thermal mixing, and at some point at very high concentration, only thermal mixing is the active DNP mechanism. This is corroborated with the fact that there are interelectronic coupling strengths increasing at higher trityl concentration. More on this will be discussed later in future tutorials. So this was the recent research on this topic. And finally, I would like to finish by thanking CRMN team in Lyon. They are all very, very helpful. And also you for attention, despite of this whatever glitch that happened. Thank you very much. Ask me questions, please.
Thanks a lot. That was really good. Yeah, I'm sorry again about the problems at the beginning. So I'm going to go in order of questions, and I'll unmute you. And so kind of pay attention. If you ask me a question, or if you typed in a question, pay attention, because I'm going to unmute you, then you can ask. So it's going to take me a second, but let me see. Go ahead, Dahania.
So my question is it possible to have quantitative spectra by DNP?
Quantitative in what sense?
So in the sense that I can integrate the peaks and have a relation of the spins, yeah, the fraction of spins of each different side in a sample.
Let me think. It is not so straightforward because there is bleaching involved. So you need to, yes, you can by careful considerations and relying on theory a bit, but you need to be aware that there is bleaching and relaxation. So bleaching is essentially when there is the nuclear spins that are very close to the electron spins cannot be observed by NMR because relaxation for those nuclear spins is very fast. So you lose those particular spins.
Okay,
You can, or maybe I'm misinterpreting. I would like to tag in one of the more experienced researchers. If you have a comment, please.
So my comment is that I know that maybe these radicals don't enhance the signal
No, they
equally
do enhance the signal.
So I mean, if you have different spins with different sides, maybe the enhancement is not proportional for all of them. Maybe that's why one could not have a quantitative spectra, but it's just, I am not expert in this, so just a question.
Yeah, okay. I can answer it in the way that if you know exactly what's the concentration of nuclear spins to electron spins, you can see how many spins are enhanced and how many are quenched by changing the concentration of radical. So you will see increase in signal at higher concentration of the radical, and at some point it starts to go down because more of the sample is being bleached than is enhanced. Also, there have been studies where they looked at particle size by looking at spin diffusion properties and to how far polarization can go in domains with boundaries.
Okay, thank you very much.
Okay, so let me find the next question now. The next person who asked was Ricarda. So go ahead, Ricarda.
Hey, I think my question is maybe a bit ignorant. It's just how do you implement the microwave irradiation in the pulse sequence? Like, or how do you do instrument-wise? Do you have a specific probe? Yeah, that's kind of my question.
Yeah, so the earlier developments have been with continuous wave microwave frequency. So what you do is just switch on microwaves, and it is being irradiated the whole time when you're recording a sample, when you're recording an experiment. So there is no correlation between the RF field and the microwave field. So RF is, as usual, pulse sequence is implemented in an experiment, and microwave is continuous in that case. However, recently there have been a so-called novel approach where pulsed DNP can be used. So you switch on microwave and then switch it off at some point. So this is more advanced. So in principle, it is possible to use pulsed microwaves, but most of the experiments are done with continuous wave DNP.
Okay, thank you.
Okay, let me find the next person. One moment. Hi, John. Please go ahead.
Oh, which question was I asking?
Oh, you had a few, so you can choose.
Okay, I guess I'm wondering about the necessity of this fluctuating hyperfine field for Overhauser effect. I would expect that cross relaxation is just cross relaxation.
Well, if you look at it from a classical viewpoint, yes, it's just cross relaxation. And this is what is applicable at low temperatures, and a broad EPR line radicals such as nitroxide under less than 6 Kelvin are known to evoke thermal mixing. That's what you mean? No,
I
you're
guess
talking about
you're talking about
Overhauser?
the Overhauser. Yep.
Yeah. I'll say it again. Maybe I missed something in your question.
Yeah, I guess maybe I missed the mechanism of why the fluctuating field is needed.
The fluctuating field is needed because there has to be a difference in relaxation rates of double quantum and zero quantum.
Ah, okay.
If not, then it's at equilibrium.
Yeah, once you drive it. Okay.
Mm-hmm.
If I'm still unmuted, how does the thermal mixing go with field?
I don't know. It is very recent, so it's a very new phenomena for MAS DNP. So it's very new in MAS DNP, the thermal mixing. Normally, we concern ourselves with the behavior of solid effect and cross effect at higher magnetic and how the developed. So, for example, these hybrid radicals tend to counter the problem of a cross effect being less efficient at higher magnetic fields. On the other side, solid effect is more efficient at high magnetic fields. So people are also trying to develop polarizing agents for higher magnetic fields, such as metal ions like gadolinium, that at higher magnetic fields should have sharper EPR line, and therefore should have sharper solid effect condition. Thermal mixing is not investigated yet in the context of MAS DNP. Thermal mixing, sorry. Does that answer your question, John?
Yeah, I just then some of us like to swim against the current and go down to lower and lower fields, and it seems sort of naively that thermal mixing would actually become very efficient in some of those cases.
It is efficient at low temperatures. I don't know about low magnetic fields.
Yep. Thank you.
Okay, let me find the next person. Go ahead, Julia. Julia? Okay. Are you there? Oh, okay. So I'll go to the next person for now. 1 second. Okay, I'll read Julia's question when she types it in, and meanwhile, I will go to Alyssa. Go ahead. Go ahead, Alyssa.
That's a really great talk. I especially liked your DMP timeline slide. That was good. When you brought up the BDPA versus Triddle, where they did the mixture of the two, I noticed that they did the SA BDPA, which is the sulfonated BDPA, right?
Yes.
Where they replaced the hydrogens with the silver. Do you remember why they did that in that paper? Because I was racking my brain, but I couldn't remember why they did the sulfonated BDPA with the Triddle mixture. It's kind of
the sulfonated BDPA has higher enhancement as compared to a normal BDPA under solid effect conditions.
Oh, okay. They were using solid.
And they eventually found out that BDPA also gives Overhauser effect.
Okay, I forgot it was solid effect that they were doing there. All right, thanks.
Okay. Just one moment. Next up is Quentin, while I find the question from Julia, because I haven't found it yet. Sorry. So go ahead, Quentin.
Hi, thank you, Monu, for the great talk. I wanted to ask you if you know if there are cases of thermal mixing using MAS, because I've only seen static up to now, and I was wondering if it is in any way possible in theory with MAS.
Yeah, it's very new, so
But
we
this
don't know.
is in static mode, isn't it?
Yes, it's in static for now. I would assume it should be possible also at spinning. Why not? All it does is modulate dipolar couplings, and at this point, there is no difference anymore. At this high concentration, there is dipolar baths of electrons and Zeeman baths of electrons interacting with the nuclear bath. So I would say that it should be possible also at magic angle spinning. I don't know, however, if it is applicable at higher temperature, so at 100 Kelvin instead of 20 Kelvin.
Okay, thank you very much.
Maybe if I ask Asif about it.
Yeah, it's a very difficult question, I think, but yes, we can talk about it.
Okay, I have Julia's question, so let me read it now. She's asking if there's a relation between thermal mixing and spin diffusion.
Actually, no. So spin diffusion is when polarization starts at one source and it propagates through a network of spins. Thermal mixing is more of a classical way of describing relaxation inside the sample. So it's looking at two very different things.
Okay, is that good? If it's still unclear, Julia, message me and we can talk about it more. The next question is from Domingo. 1 second, I'll unmute you. Go ahead, Domingo. Oops. Sorry, the button's not working.
Can you hear me now?
Now it's working. Yeah, now it's working.
Okay, so thank you so much for the presentation. Was so good. And I wanted to ask you, how does the polarity, viscosity, or the optical clarity of the solvent influence the signal enhancement of the sample that you are measuring?
That's a very good question, and it does influence a lot. So, for example, if the first thing is optical clarity. As long as it is transparent to microwaves, it does not make a difference in how the signal is enhanced. Viscosity under magic angle spinning should not play a role because it is a frozen glass. So it doesn't matter how viscous the sample is. If it is a frozen glass, it behaves like a glass. Polarity, we can do experiments on organic solvents, polar as well as apolar. Maybe, do you mean to ask conducting samples? Sometimes there are samples that are magnetic in nature. They tend to have problems spinning in mass setup because they tend to be influenced by the magnetic field inside the magnet and go towards the coil. So, but signal enhancement, that does not it does not have any effect on signal enhancement. Probably dielectric particles can, not probably, for sure, dielectric particles increase microwave penetration and distribution in the rotor. Therefore, there is enhancement in the signal because of dipolar dielectric particles. Yeah.
And why did you choose, I think, the mixture with water and glycerol? Why don't you choose just water instead of this mixture?
Because it forms ice crystals, and a radical in some kind of crystal cannot polarize another crystal. So in DNP, we want a uniform glass so that the polarization can go through a network of spins instead of being restricted by some kind of boundary domains in ice crystals.
Okay, thank you.
Thanks a lot. I have a question from Vinay. They asked me to read it. So the question is, the Oberhauser effect has an absorptive mid-peak while thermal mixing has a dispersive mid-peak. Any comment on it?
Yes, so Oberhauser works with zero quantum or double quantum transition rates. With zero quantum, it gives a positive signal. Double quantum, it gives a negative signal. Thermal mixing, I don't have a field profile for thermal mixing in mind. And I assume that, wait.
So I think that in thermal mixing, you would get a dispersive one, kind of like the green one you're pointing at. It comes from a mixture of, you form a temperature across the EPR line. Some electrons have a higher than zero and some have a lower than zero temperature. And then if that's also the temperature of the nuclei, then that means that they're also, some are above zero and some are below zero, meaning some will be positive and negative.
Okay, thank you, Datna. I'm not very familiar with thermal mixing. I just put it in because I wanted to show the recent development in case of DNP mechanisms.
Sure, no problem. And actually, Vinay had another question. So the second one is the DNP uniform over the sample and over the different nuclei?
Say it again.
Is the DNP enhancement uniform over the sample and over the different nuclei?
It generally should be uniform over the sample if we have a perfect amorphous glass. It is not uniform over different nuclei because it scales with the gamma ratios. So it is just like cross-polarization. For example, enhancement on carbon should be 4 times higher than on proton, because the gamma between gamma E divided by gamma N is the enhancement. So it is generally high for carbon and it's even higher for nitrogen and so on.
Okay, there's a clarification. They mean that if the nuclei are the same type of nuclei, but at different sites in the molecule, will they have the same enhancement?
That depends on the distance from polarizing agent and on motions. If one of the domains, for example, is more mobile, then it would have lesser enhancement as compared to the one that is rigid.